We're going to take a more general look now at first-order systems, particularly first-order systems that don't have any zeros. So down here I have a transfer function g of s in general terms with a divided by s plus a. So no zeros and one pole. We notice that the highest order term here is s to the 1, so that's why we can say it's a first-order system. And again, we have our input r of s and our output c of s. So we can represent this in our complex s-plane. So we have our sigma, or our real axis, and our j omega, which is our imaginary axis, and we have one pole at a point negative a. So we could come in here and we could indicate that with an x at point negative a. So just like we did last time, let's assume that we have a step input. So assume a step input. And so what that means is that our r of t is u of t, so our r of s is 1 divided by s. So then we have our step response, which is going to be c of s is equal to r of s times g of s. So in this general case, we have a divided by s times s plus a. And so the result of this, as I said before, is our step response. So that's important terminology just to kind of be familiar with. And if we were to solve for that, what we get is our c of t, our step response, is equal to our forced part, cf of t, plus our natural part, cn of t. And it turns out that that is equal to 1 minus e to the minus a t. So we get something that looks like this for our step response. So we can plot that. So if we plot that, we have something that looks like this. So I've got c of t on my vertical axis here and t on our independent axis. And so we see it's starting at 0, and then as that exponential goes away, as our a gets larger, or rather as our t gets larger, that exponential term is becoming negligible and we're approaching 1. So a couple important things to note is that a is the only parameter that is needed to describe our transient response. So a is the only parameter needed to describe our transient response. So because of that, we give it a special name. Catch up with myself here. And so because of that, we can call our a the exponential frequency. And so one thing to note too is, of course, we can talk about multiplying our transfer function by a constant value, but that's only going to change the amplitude, not the behavior of our system. So not the form of this unit response, we would just get a scaled version of that. Okay, so now what we want to do is, now that we know that a is the only parameter that we need to know, let's look at how we can describe some of our performance specifications. So we want to describe performance specifications. And so the idea with this is we could say this system has a specification of this in this area and this in this area, and that makes it easier to quantify the behavior of the system as well as sort of compare it to other systems. So the first thing that we're going to talk about is something called the time constant. So our time constant is just the inverse of that exponential frequency, so 1 over a. And so because a is a frequency, dimensionally this 1 over a, as expected, is going to be equal to seconds. And so the equal sign with the d over it just means I'm talking about dimensional analysis for that 1 over a term. So this is going to be related to the speed that our system responds. So it relates to system response speed. Okay, and so that's response to the input r of t. And so a way we can kind of get a better grasp of this is, let's say we evaluate that c of t function we found above at a value of our time constant, so at t equals 1 over a. So if we plug that in, we have 1 minus e to the minus a. Now for t, we have 1 over a. So of course that becomes 1 minus e to the minus 1. And so evaluating that gives us approximately 0.632. So what our time constant means then is our time constant is the time it takes to reach about 63% of the final value. Okay, so that's what our TA is. So what we can see from that is that if our A is further to the left in our S-plane, then we're going to have a quicker response. So further left in our S-plane corresponds to a quicker response. So for example, if we had a pole at -2, so coming back up to our S-plane here, let's say that this A value here is -2, we would have a time constant of 1/2, and our response would have some, in 1/2, it would reach 63% of its final value. However, if we move that pole further left, so now let's say this moves to being at -10, this A, then we would have 1/10 for our time constant, and we're going to be at 63% of our value in 1/10 of a second as opposed to 1/2 of a second. So the further left, the faster our time response is. So let's go ahead and update our plot up here. So about 63%, so we can say that would be about right here is where we have 1/A. So this would be 1/A right here, and that's our time constant. Okay, so let's define a couple other important things. The second key metric for specifying performance is something called the rise time. And so our rise time is somewhat arbitrarily defined as the time it takes for our signal to go from 10% to 90% of its final value. So time to go from 0.1 to 0.9 of the final value. And so we're going to do a similar thing as we did with our time constant. We're going to evaluate our C of t at those 2 points. So we can say C of t evaluated, or not evaluated at, but set equal to 0.9, and then solving for t2, we see that that is negative log of 1 minus 0.9 divided by A, and evaluating that we get approximately 2.30 divided by A. Similarly, if we set C of t equal to 0.1, we can call that T1, because that's of course going to happen sooner. That's why I'm calling that T1. So that is negative log of 1 minus 0.1 divided by A, which is approximately 0.105 divided by A. So now our rise time, as I've stated above, is defined as the difference of these two times. So we're going to call this T sub r. We're going to say this is T2 minus T1, which is approximately 2.2 over A. So this is our rise time. So we can update our plot with that. So 2.2 over A. So we have something up here in our plot. So let's go ahead and say so here's our 90. And so of course this isn't going to be perfectly to scale, but basically from here to here is going to be our rise time T sub r. Okay? Sorry, so I have a lowercase r, so let me be consistent with my notation. So that's our rise time T sub r. And so that's a little bit more than 2 over A, so let me just roughly say this is 2 over A right here. The other important metric that we have is something called settling time. And so this is the last one we're going to look here. And so this is the time for our response to reach and stay within 2% of the final value. So time for response to reach and stay within 2% of final value. And again, this is somewhat arbitrary. You might see settling times, 5% settling times or 1% settling times. So choosing this 2% is relatively arbitrary, but something that's typically done, which is why we're looking at this first. So what we can do is we can say C of t is equal to 0.98, because for this particular function, using this C of t up here, looking at it graphically or the equation, we can see once it gets within 98%, it's not going to be deviating. It's not oscillating about that final value. So we can say C of t equals 2.8 is going to give us our settling time. So t is equal to negative log of 1 minus 0.98 divided by a, which is approximately 3.91 over a. Now we can take a conservative estimate for this and we can say settling time is approximately 4 over a. So again, that's a conservative estimate. Okay, so let's update our plot. So again, not necessarily drawn great into scale, but let's say about here is our 0.98 or 98%. So we get something about here would be our 4 over a, again with our conservative estimate. So of course somewhere between 2 over a and 4 over a is 3 over a, and this time from 0 up to 4 over a is our settling time t of s. So these would be our important metrics. So remember, we have our time our time constant 1 over a, our rise time t sub r, and our settling time t sub s. So keep in mind though that all of these parameters and equations that are boxed here are only for our first order system with no zeros. One other thing that I want to mention briefly is what do we do if we don't have an expression for g of s? So what if no g of s expression is available? So maybe think about that for a second and think about what you might do if you had the system available physically, but you didn't know what the expression for g of s was. So what we can say is, we could say, let's make an assumption that it's a first order system. And what we could do is we could input a step input. So give it a step input, and then measure time for it to reach 63%. So measure time for system to reach 63% of its final value. And then of course, once we know that time for it to get to 63% of the value, we know our time constant. So remember, our time constant is just 1 over a. So from there, we know our a, and then we can figure out our settling time and our rise time from these equations shown here. We can also figure out any constant value that's being multiplied by that transfer function. For more details on that, you can see pages 136 and 137 in the 8th edition textbook. And essentially, we're not going to worry about that too much, but I like to have you all keep in mind that we can also take these ideas and apply them to physical systems. We're not just sitting here talking about equations. So in terms of thinking about what does this mean when it reaches 63% of the final value, well, we could be talking about a voltage in a circuit. So maybe we measure it and we see when it reaches 63% of the final value. Maybe we're talking about the position of some component in a mechanical system or the speed of some component in a mechanical system. So there are a lot of different systems that these ideas can apply to.